Okay, so good afternoon, everyone. Right, so this is the second compulsory day school of CYU 4301, and this will be the last compulsory day school for this particular course, right? So, therefore, ask your friends if you haven't joined so far. Ask your friends to join quickly possible, right? So, um, now, let me introduce myself. I'm Dr. Dushanta Alvid. So, some of y'all may know me, right? So, even yesterday, y'all have participated the first part of this day school. So, that is done by Dr. Asela, right? So, let me share this small introduction. Those who haven't participated last day school, right? So this course is level 4 3 credit course. So how many notional hours that you all should spend for this particular course? How many notional
150
hours?
hours.
Very good. 150 hours you have to spend on this, right? So this consists of the concepts in chemistry. That means the most important concept of the chemistry is in this course, right? So therefore, it's very really important for you to study this course very properly. Otherwise, you might have heard from some of your seniors might have told you this course was very tough one. No, it's not such difficult parts are there, right? So what you really want is your interest, as well as you have to spend a minimum, at least minimum number of hours on this, right? So most of the physical concepts is covered in this particular course, right? So I'm Dr. Dusanta Alvis, and I'm the senior coordinator, one of the senior coordinator of this course, and Dr. Asela Dikkumbara is the another senior coordinator. So myself and Dr. Asela will be there as the senior coordinator, and also we have in the teaching panel Dr. Kumudika Jayalat, right? So we are the coordinators, right? And here this course consists of 4 units, right? So what are those 4 units? The first unit covers the spectroscopy part, which consists of 7 sessions, right? And I myself will be doing this spectroscopy. And yesterday you were able to participate for the kinetics one, right? So that is covering by Dr. Asela. And your unit 3 consists 6 sessions, which will be covering by Dr. Kumudika. And we have phase equilibria, right? So again, myself is doing unit 1 and unit 4. So today now I'm covering unit 1 and unit 4. So with the molecular spectroscopy as well as phase equilibria, right? So those two are not only those two, even chemical kinetics, electrochemistry. So most of the concepts is covering in this particular course, right? So these your course, I mean, you might need these knowledge when you are doing your research, and even suppose you are doing other physical chemistry advanced stuff, if you will get selected for the special degree. So these things are really important for you, especially when you are doing research. It's important. The physical chemistry concepts mainly covered here, right? So you all know the day schools are the interactive session. So I hope you all can answer my questions, so you can give me few questions if you have, right, to get clarified, right? So likewise we will do this interactively, and you can refer the information sheet which I have already uploaded into the email, or I have uploaded to Telegram group, right? And so these 4 units, the soft copies of these 4 units, I will put it in Google Drive and give you the Zoom link, right? Google Drive link will be given you so that you can read these books, right? And otherwise, just after the compulsory day school, you better have go through these course materials as well. Now, since this non-academic, the trade union action is going on, you might not be able to get the hard copies, but probably we will we are we will think that this will be over by this week, right? So in that case, after the registration, you will have to do your official registration, as well as your course materials can be collected after that, right? So please refer the information sheet very clearly. So this consists of 2 CATs and 1 final exam, right? So the CAT 1, for the CAT 1, remember all 7 sessions will be covered, and unit 2, sessions 1 to 5. So all 2 units will be covered for the first CAT. And second CAT, unit 3, 1 to 6, and unit 4 again 1 to 6, right? So final exam consists of 2-hour paper for questions, one from spectroscopy and the kinetics and electrophase equilibria. So likewise, you will get the final examination paper. And your eligibility mark, OCAM, should be more than 35, equal or more than 35, right? So the best from the best assessment, 0.6 and 0.4 from the remaining test mark, right? So that's how the introduction, you have already obtained this yesterday, right? So let me share very quickly the presentation. Okay. So hope you all can see my presentation. Is it clear? I mean, here, can you all see this presentation slides?
Yes, ma'am.
Right. So everyone should speak. Okay. So now here, this is your first unit. Unit 1, how molecules produce spectra, right? So the absorption of electromagnetic radiation by matter, right? So here we are studying how the electromagnetic radiation, that means you have studied during your level 3, the electromagnetic radiation. What is EMR? Electromagnetic radiation. Huh? What is electromagnetic radiation? Hurry up quickly. Have you studied it at your level 3? Have you studied EMR, electromagnetic radiation, when you are in level 3? Huh? Can
Yes,
you all
ma'am.
hear me? Right. So you should answer, right? Okay. So now electromagnetic radiation, how it interacts with matter, right? So you all know when the sun's light come into the earth, right? So what will happen? There can be, sun is the primary source of energy, right? So sun as the primary source of energy, it consists of, have you all seen the sun spectrum, the electromagnetic spectrum of the sun? So which area it absorbed more? Huh? So what is sun's electromagnetic radiation? What are the maximum wavelength that it can absorb? Sun rays gatto? What is that? So you all should know those things, right? So you all know mostly UV and visible range. the sun's energy consists of that range, right? Other than the other slight radiations, right? So the sun's energy is really important, and when it interact with matter, so that is another natural phenomenon occur in the world, right? So without that, none of us can exist, right? So what, give me one example to how electromagnetic radiation interacts with matter. Give me one example, the most important example in the world.
Photosynthesis.
Very good. Photosynthesis. What will be happen there? So you all know the sun's energy is coming towards the tree, right? So what absorbs that sun's energy?
Chlorophyll.
Chlorophyll. Yes, chlorophyll inside the plant can absorb sun's energy, right? So these are two different words, absorption and another terminology, adsorption. What is the difference between absorption and adsorption? So you all should know those things, right? So sun's energy can absorb by chlorophyll molecule. So which color you can observe the chlorophyll molecule?
Red and blue. Green color.
Green color. So why it is green color? Why is it green color?
It
Because
absorbs other colors in visible rays and reflects only.
the visible light range
Yes,
has
very
not
good.
observed
That
it.
is because it absorbs its complementary color, right? So let's go somewhere down, right? So you can give here several examples. So not only photosynthesis, when it comes to the solar energy systems or some other, there are several ways that we can give you the examples. Electromagnetic radiation interact with matter, right? So here, this is the sun, the importance of solar energy. This is sunlight. So what will happen when it comes down towards the earth? So certain amount can be scattered. So 20% scattered and reflected. So what is scattering? What is reflection? There are two important terminologies, scattering and reflection. 20% can be scattered by clouds or reflected by clouds, and 51% can absorb by earth, right? So I mean, there are several phenomena where the sun's energy can absorb by the matter or the earth, right? So certain amount can again reflected, 4% can again reflected, and 19% can absorb by clouds or atmosphere, right? And 6% can scattered from the atmosphere, right? So you should come into your mind, it should come to your mind how the rainbow appears. So that is again the one of the phenomenon happens, interaction of matter and radiation, right? So light is in everyday life, so it is very important to study how the matter interacts with electromagnetic radiation, right? Okay, so these are some other examples. So as you all have given me the photosynthesis, so why it is important? Example, huh? Why the photosynthesis is an example for this? So in this process, in the photosynthesis, plant can convert energy from suns to chemical energy. What will happen? The water and carbon dioxide converted into glucose here, right? So this is the chemical. It converts the sun's energy to glucose, right? So what is the structure of chlorophyll molecule? In which range it absorbs? Huh? Which sort of structure does the chlorophyll molecule contains? Let me quickly get the
It's
structure.
green in color, therefore it should be in the visible light. 400 to
Yes. So
700
why it
nanometer.
absorb visible color? Why not IR or UV? Huh?
Green in color, green chlorophyll is green.
Yes, you have chlorophyll A and chlorophyll B, right? So why it specifically absorb green color?
Because the electrons on that chlorophylls matches with the frequency of green color range energy to create glucose
Okay,
molecules.
somewhat okay your answer, right? So let me share the structure of chlorophyll molecule. One second. Okay, let me share this. Right. Hope you all can see the structure of chlorophyll, right? So this is the structure of chlorophyll molecule. You have several double bonds. The conjugated system is also there, right? So that absorb in the frequency of visible range, right? So that's what this particular molecule, it absorb energy from visible range. So that's why you can observe. So which range it absorb? What is the range?
Bomb.
Yes, it's absorbed the red color. This is the complementary color. Here, our plant is green in color. So what is the complementary color? The other side of this circle. You have this range, red and orange, right? Absorbed by the chlorophyll molecule, right? So that's why this range can absorb by chlorophyll molecule. So that's why the complementary color of it can gives you to your naked eye. So that's why it's in green color. The rest is reflected, right? So that is reflection. Okay, so now appearance of color of an object can be explained by using the interaction of electromagnetic radiation with matter. So, can I ask one question? What is the color of sea? Why you can observe the color of sea or it's in blue color? So, you should be able to explain that, right? Why the sky is blue in color? Right? So you should be able to give answers for all these things. So all those explanations can be given by using the interaction of matter and electromagnetic radiation. Right? Is it clear? Okay. So this is another example. What is happening here? So heating by sunlight. So this is a heater. Inside a home, you can have heaters, right? So what will happen here? Which absorbs sunlight here? Huh?
Solar
What is
panel.
this? Yes, you have here solar water system, right? So what will happen inside the solar panel? What is the theory behind that? What do you have in a solar panel?
Silicon.
Hmm? What else? Hmm? What does it consist of? I mean, yeah, the solar panels. Huh?
Heat
Silicon
energy,
Convert the light
molecules.
energy into electrical energy.
Okay. So what is
It is
absorbed by the in solar panel? How the energies can absorb by solar panel? So here in the solar panel, you have titanium dioxide as a adsorbent, right? So here you have TiO2. So the TiO2 molecule, right, can adsorption. So this is, it happens, the adsorption surface phenomenon. It's a physical phenomenon, that is adsorption. So your dye molecule, so it can be a natural dye or a synthetic dye. Dye molecule can absorb into the titanium dioxide particle. So which can absorb solar energy? Huh?
electrons.
Yeah. What is the molecule here which can absorb solar energy?
Titanium.
Not titanium. What is that? So your dye molecule can absorb solar energy. So that is absorption, right? Okay. So this is absorption. So your dye molecule can absorb solar energy. And if it is a natural dye sensitized, we called it as dye sensitized solar cell. Right? DSSC. Dye is as the sensitizer. Right? So what will happen? What is sensitizer? Which is the one which can absorb the solar energy. Right? And then its electron can transfer into TiO2. So what will happen inside the dye molecule? You have a ground state and excited state. Once that dye molecule absorb energy, so let me start from here, right? So once this solar energy comes towards the dye molecule, the electrons in the ground state can excited into its excited level, right? So now here it's electron in the dye molecule. This is your dye molecule. It can be a natural dye like carotenoids, right? So certain carotenoids can absorb the solar energy, and that is why we called it as dye as a sensitizer, right? So what will happen? And then this electron. So here in your TiO2 molecule, what are the energy layers you have? You have a conduction band and a valence band, right? So this electron can come to the valence band of the TiO2 molecule. This is your TiO2, titanium dioxide molecule. So that electron can again go to, has to be this, right? Give me 1 second, right? Valence band and the conduction band, right? Okay, so now this electron can go to the valence band of the titanium dioxide molecule, right? And from there again, it's going down. So likewise, inside a solar cell, this electron transition can take place, right? And then this will become, you have two layers like this. So you better go through the solar cell system, right? So that's why it is very important to study all these interactions of matter with electromagnetic radiation, right? So all the phenomena, most of the phenomenon in our life will based on this, right? So go through the solar system. What is happening inside the solar system? So now sun's rays can come here and it can convert into electricity inside a boiler, right? So that's how you can get hot water from here, right? So that's what it's very important to study the interaction of electromagnetic radiation with matter, right? Okay, let me quickly move down. Right. So now here you have two entities. What are those two entities? Electromagnetic radiation and matter. Those two can interact each other, right? So it is necessary to refresh your memory first about the electromagnetic radiation and also the matter before you are studying their interactions, right? So that's what we are going to do next. You have any questions up to now, Marsha?
Madam, what is the difference between absorption and adsorption?
Yes, absorption means it can, the molecule, suppose this is the molecule, the carotenoid molecule, that can absorb light here, right? And this is the absorption, right? However, when it comes to the titanium dioxide molecule, right? PiO2, this the dye molecule can absorb that surface phenomenon, right? So this surface decata, it can absorb the dye molecule. It's a physical phenomenon, right? Surface chemistry, when you are studying, when you come to your special degree, if someone suppose do special degree, you will be able to study all these things. So that is the surface phenomenon. That can be the with the interactions here. It can be hydrogen bonding or van der Waals interactions, right? So that is absorption, right? So this is the energy absorbed. So can you take one example? K-menophorm solution. So it can absorb energy, and the remaining rest is coming out from the solution, right? So some amount can absorb. This is again absorption, right? Okay, where this is where we apply the Beer-Lambert law. A is equal epsilon CL, right? So that is the Beer-Lambert law where we can observe the absorption, right? So this is the absorbance. Okay, is it clear now?
Okay, madam.
Okay, any other questions up to now? Okay, right. So let's see first of all the electromagnetic radiation, right? So it's a electromagnetic radiation consists of waves. So can you all remember? You have studied this. So what sort of electromagnetic spectrum we have? What are the range we have? Radio wave, microwave, infrared. Here this is the visible range. So what is the visible range? The wavelength of the electromagnetic spectrum. Visible range lies in between. What is the
400
wavelength? 400 nanometer to
800 nanometer.
400 to 700, right? So nanometers. Or 8 to 700 wage range again, right? So that is visible. And you have UV. So your sun's energy. So, you can search. So you have, internet facilities. If you have internet, you can, go through the sun spectrum. So which sort of spectrum is that? වැඩිපුර sun's energy මොනවද තියෙන්නේ?
Visible and UV.
Let me quickly show you. Right? So let me share this. Hope you all can see this. right? So here, your sun's spectrum is like that, right? Spectrum of solar radiation, right? So it consists of 250 towards, it's on the mostly visible UV and certain amount of IR, right? Have you all noticed so far? Huh? Have you all noticed so far you have certain amount of UV, you have certain amount of visible and IR radiation in the sun's energy, sun's solar radiation. Do you know about that? Right? So this is how the sun spectrum. So it absorbs the maximum. What is the lambda max of the spectrum? Huh? What is lambda max here? Hurry up quickly. Which range it lies? Around 500 nanometers.
Well, like,
Huh? Is it clear? Is it clear, everyone?
Yes, ma'am.
Right. Okay. So now let's see this particular spectrum. Here we have the radiation, radio, right? So we have radio, microwave, infrared and visible UV, right? So when it comes to this side, what will happen to the wavelength
it's get
and the energy?
Wavelength
decrease.
decrease.
Energy increases.
Wavelength
Wavelength decrease and energy also getting less.
Yes, wavelength decreases. And what happened to the energy?
Energy also decreases.
Energy
Energy
increases the
increases.
Energy increase.
energy increase. Can you remember the Planck equation? E is equal H name, E is equal HC over lambda. Huh? What will happen if this is low? Energy මොකද වෙන්නේ? Increase.
High.
Right? So when you go towards this end, that means gamma rays has the highest energy. And next is X-ray. When you're going towards the radio wave, it has the lowest energy and highest wavelength. Right? So that's how the molecular spectroscopy lies in between. So have you heard about the UV visible spectroscopy? Huh? That means it absorbs this range. So if it is IR spectroscopy, that absorb interact matter with IR spectra, IR region. And if it is microwave spectroscopy, that can absorb this range, right? So that's how the different spectroscopies can have different absorption of the electromagnetic radiation. Is it clear now? Is it clear?
Madam.
Others?
Yes, madam.
Madam.
Okay.
Yes, ma'am.
Right. Okay, so now let's see the electromagnetic radiation. Can you all remember? One time it exists as a wave. Here, the wave nature of the electromagnetic radiation. Can you all remember? You have studied the wave particle duality of electromagnetic radiation. Huh? It can
Yes.
once it can as a wave, and sometimes it can behave as particles, right? So we call this as wave particle duality, right? So the electromagnetic radiation can one time as a wave and also it can be a particle. So when it is a wave, we can use this equation. C is equal nu lambda. If you know the lambda is from here to here, the distance O from here to here, right? So if it is a wave, we can apply this C is equal nu lambda. C is the speed of the light and nu is the frequency. So, and lambda is your wavelength, right? Okay. So, and also it can be a particle nature, right? So here the electromagnetic radiation. So this particular radiation can have lot of particles in it inside, right? That means a beam of electromagnetic radiation consists of a stream of particles. Those particles we called as photons. That's how the photon energy, H nu, right? So these particles can have several energies, depend on the nu, depend on the frequency. It can be in the UV range, it can be visible range, it can be IR range, or it can be microwave, right? So all depend on the frequency, depend on this frequency, these particles can absorb by certain molecules. If your particular molecule like chlorophyll, which can have conjugated system, right, can absorb in the visible range, right? If your molecule has N to 5 star, some other transition, that can absorb the UV range. It's all depends on the frequency or the photon energy of a particular of this particle, right? So these particles are called photons, which travel at a speed of c, right? So here we can apply this E is equal h nu, the Planck equation, when it behaves as a particle, the particle nature of the electromagnetic radiation, right? E is energy, nu is frequency, h is the Planck constant, right? So now you can understand very clearly the wave particle duality of the electromagnetic radiation. So it's very important, these phenomenon, to study the spectrum of, or the spectroscopy, the molecular spectroscopy. That's why we called it as molecular spectroscopy. So this is really interesting to study all these interactions, right? Isn't it? Huh? How many of y'all would
Yes,
like to
madam.
bring? Yes, that's what. How many of y'all would like to study further molecular spectroscopy? Please raise your hands using raise hand option. I would like to see. Good. Oh, mechcherada. Huh? Only 5 people in this class, in the whole class. 175 we have here. Huh? Other? Good. Only these few. I want everyone to study molecular spectroscopy. It's really interesting. Apply your phenomenon. I mean, the naturally occurring phenomenon is there. Only very few in the class. Huh? Would like to study the molecular spectroscopy. Others, what will happen? Let's see. We have Nisansala, Manoj Buddhika. You don't want to study molecular spectroscopy? Hmm?
Yes, I am,
I
madam.
don't. You don't want to study a molecular spectroscopy? Huh? කැමති නැද්ද study කරන්න? Huh? Manoj? Manoj නේද මම දැන් කිව්වේ?
Yes,
Huh? Yeah, only
yes,
42
madam.
participants, right? Anyway, those 42 participants, might wanted to study the interaction between molecules and the electromagnetic radiation, and there are several research also we have. I mean, when we are doing research, also these stuffs can be important, right? So, for example, I'm also involved in with mostly carotenoids, study of the carotenoids. Carotenoids as dye-sensitized solar systems, right? So it is really interesting to study all these research, and even when you come to your higher level, this will be important, these concepts, right? So, okay, now you all know the dual nature of wave and a particle duality of electromagnetic radiation, right? Okay, let's move down. Right. So now we know about the electromagnetic radiation, right? So it has a wave one time and also has a particle, right? Let me, okay, right. So now the matter, let's see how the matter is there. The matter consists of molecules. So you close your eyes and go inside a matter. So you have given a small piece of, let's see, a ice cube. Or even, let's see, it's dissolving now. So we'll take one, a piece of, what's that? A piece of a matter, right? So it's it's uh, a brick, a piece of brick is given. So you close your eyes and go inside that, right? So when you go in, you can observe which is the smallest particle. The atoms, or there can be molecules, right? So molecules made up with atoms, right? So the matter consists of molecules. So these are the molecules. There can be propanol molecules in your solution, propinal solution. Take a matter. So that can consist of these molecules, right? So the energy of a molecule, what sort of energies that it can have? This propanol molecule, huh? Is it a range of energy? Does these molecules have range of energy?
No, it has a
No.
particular
Huh?
energy.
Certain
It's not a range. The energy of a molecule is quantized. We called it as quantization of energy, right? So what is the meaning of quantization of energy? That means it has a specific energy values. So here you have E1, E2, specific values, E3, E4, right? It's not a range like this, right? And so we called it as the quantization of energy. Within the molecule, inside this molecule, the energy levels are quantized. So we called quantization of energy. So depend on the energy difference. So let me, first of all, I'll explain this and we'll go to that, right? Otherwise, you might not understand, right? Okay, so the quantization within the molecule. So the matter consists of molecules, and within the molecule, it has energy levels like this, right? So it has energy levels like this. And energy of a molecule is quantized. We called it as quantization of energy, right? Okay. So now this is, now come to the absorption, right? So let's see, this is still we are in the macroscopic wave, right? That means, what is the difference between macroscopic and microscopic? That means you have in your mind you can visible it, the macroscopically it's you can observe the certain, when you put incident beam having I naught energy into the absorbing sample. Suppose this is Kmn of a sample, right? Suppose this is your Kmn of a solution, right? So what will happen? It can absorb energy from the incident beam, right? And the remaining can go out. After absorption, right? It's depend on the molecule energy difference, right? Certain amount can absorb and the rest can go out from the solution, right? So this is the absorption. So this is absorbing sample. Yeah, in this case, it is KMnO4, right? Okay. So suppose this I naught is the incident beam intensity. I is the beam coming out from the sample solution, right? So what will happen here now? Here, so this is the last compulsory day school. Do not ask your friends. This will be the last one, right? Ask them to join here. Otherwise, we will be taking your attendance, right? So if these attendance are not there, compulsory day school means you have to attend. You should attend. It is compulsory for everyone to attend, right? I will give you quickly 1 minute. Please put your registration number within bracket your center into the chat. Quickly, now itself we have 175 participants here, right? Madam, is this technique used frequently in biochemistry and pharmaceutical chemistry research? Abhishek. Abhishek, you have given me this question long time back, but now only I have checked my WhatsApp. Can you, Abhishek, you need to explain more about this? Huh? I hope when if you have any more clarification, please ask, right? Okay, so you can put your name and within bracket center, sorry, registration number within bracket center into the chat box, right? Okay, so let's move down. Your friends cannot complain because this will be where we can accommodate 500 participants in this Zoom link, right? So hereafter, we are not going to have this type of compulsory one, right? So only after the ad drop period, we will have only for the ad drops people, right? And people, this particular course, right? So make sure your friend is attending this. Okay, because this knowledge is really important for you to study further, the spectroscopy. Not only the spectroscopy, all 4 units like that. Okay, right. So what is meant by intensity? What is intensity? What is intensity? Huh? What is meant by
Energy
intensity?
across
Okay. Yes, Sumudu. Tell me what is
energy
intensity?
across unit surface area at a unit time.
Yes, intensity is energy flowing through a unit area per unit time, right? So It is given this particular unit area per unit time, how much of energy passing through there is called the intensity, right? Energy flowing through unit area per unit time, right? Okay, so now we are still in the macroscopic view of matter and electromagnetic radiation interaction, right? So we see the whole macroscopically, we see what will happen. The color, once the colored solution is there, when we passing the intensity I naught and the beam coming out is I. Certain amount can absorb by this, right? So suppose you have given a path length B, right? And the concentration of your Kmin of a solution is C. So in that case, what happened to I? Right? What happened to I when B is increased? If B increased, what will happen? The path length increase?
Intensity decreases because of
Intensity
the
decrease.
absorption of the solution molecule.
He's telling it decreases. Any other answer?
Increase.
Intensity increase. I'm asking I. Any other answers other than these two?
Decrease.
Decrease. Any other answers? What will happen? Decrease or increase?
Decrease.
It
Decrease.
should be decrease. Why? So when I naught is constant and path length is B, C is again constant, right? So what will happen? In this concentration, you have several molecules like this, right? If you increase the path length, that means the number of molecules you have is again increases, right? So that means several I naught, the beam of I naught can absorb by lot of molecules. So the beam coming out can be decreased, right? So your answer should be decrease. So now what will happen? The C is increased. Concentration
I
increase.
will decrease.
Sorry, C
will
decrease.
I will decrease.
C decrease.
I
Una?
decreases.
I decrease.
Decreases.
I decreases.
Increases.
I increases. Due to
Ah.
the
I decrease.
concentration
Ah.
less mean
Large
molecule
Which
particles
answer?
number of particles are less. Therefore,
Which
I
answer?
will be increased.
The concentration
Yeah.
is high, the number of particles will be high, therefore they can absorb more. Therefore, I will decrease.
I'm asking if C decrease.
I will increase.
Increase.
I will increase.
Increase, ma'am.
I will.
decrease. Decrease.
Which
I
answer?
will
Kawada mama දැන් කාගේ answer එකද I'm considering? Which answer do I need to consider?
If
The
concentration
concentration is high,
decreases,
the number of
Okay.
particles will
intensity
be less.
increases.
Therefore, only less amount will be absorbed.
Okay.
Therefore, I will increase.
Yes, I should be increased. Here, concentration decrease means very little number of particles are there to absorb your radiation, right? So then what will happen? The beam coming out, the intensity of beam coming out can be increased, right? So this is your answer. Is that clear? Clear there?
Yes, ma'am.
Yes, ma'am.
Right. Okay. Right. So these are the answers. B increase, I decrease. C decrease, I increase. Right? Okay. So now we are still in the macroscopic wave. Right? Macroscopically we see what will happen. And now it says the Beer-Lambert law. That's how the absorption we are studying is applicable for the molecule which can absorb energy. So we can use the Beer-Lambert law for certain with a certain range, right? Can you all remember? So what is the range where you can apply the Beer-Lambert law? 0.2 to the absorption මොන range එකද? 0.2 to 0.7 විතරයි. Why? It is because after 0.7 what will happen? Huh? This can be deviation, right? So it can be positive deviations and negative deviations, right? From the Beer-Lambert law. So you can apply the Beer-Lambert law for the molecules absorbing this range 0.2 to 0.7, right? So the Beer-Lambert law, application of Beer-Lambert law, you can study even in your practicals and even for the theory part, right? So you better refer those things, right? So here, what we are going to do? So here you have the same molecule, I naught the incident beam, and I is the beam coming out, path length B, and concentration C here, right? So what is your Beer-Lambert law? What is the Beer-Lambert law? A is equal minus log I over I naught, right? So what is A? Huh?
Absorbance.
Absorbance.
Absorbance, right? Absorbance, right? So, buns. And what is I? I is this. I naught is the incident beam intensity, right? So, what is I over I naught? What is this value? Huh? That is called transmittance, right? So, that means A is equal minus log T, right? T is your transmittance, right? So, in the other hand, so the Beer-Lambert law gives you equal epsilon CL, right? So, this is the Beer-Lambert law, right? Okay, so now where the epsilon, what is epsilon here? Huh? What is epsilon here?
Molar extinction coefficient.
Molar extinction coefficient or molar absorption coefficient, which depends on the frequency of radiation. That means the epsilon is changed if the frequency changes. That means suppose you are sending a beam having the frequency, the visible UV range, right? So your molecule can absorb a certain amount of energy. So suppose you are going to change the frequency to visible, right? Visible light එකක් එව්වොත්. So it can absorb some other amount of energy. So epsilon is depend on only on the frequency of the beam, right? So which depends on the frequency of used, and hence A is the absorbance, right? A is called the absorbance. Is that clear? Is it clear now?
Yes, madam. Yes, madam.
Okay. Right. So now let's see
Excuse me.
what happens to A. What happened to A when B increase? B is going to increase. These are constant. I note constant and C constant. What will happen to A? What will happen to A when B increase?
Increases because
B increases now?
the length.
Huh?
Then when length is increased, absorbance increases.
Any other answer? Hmm? කො අනිත් අය?
Absorbance is increased.
ඔයාලා දන්නවා නිදාගෙන ඉන්න කට්ටිය. කාලා බීලා හොඳට නිදාගෙන ඉන්න කට්ටිය කොබල නැත උස්සන්න. Hmm? Huh? කවුද මේ අත උස්සන් ඉන්නේ? නිපුන්. නිපුන්. කලින් raise hand කරපු ඒවමද කොහෙද තාම තියෙන්නේ? නිපුන්, can you hear me? නිපුන් සමරසිංහ. Hmm? Can you hear me, නිපුන්? Can you hear me? Okay. ඔන්න නිපුන් අහුණා නිදාගෙන ඉන්නවා, right? So let's see next time. Okay. So now what will happen to A when B increases? You all know the Beer, according to Beer-Lambert law, A is equal epsilon CB or CL, right? So that means what will happen if B increase? A also increases, right? So what will happen to A when C decrease? C decrease करो, ඒට මොකද වෙන්නේ?
A decreases.
Decrease.
Decreases.
Decreases, right? So likewise, if you should be able to study or you should be able to explain what will happen to the absorption or the absorbance A value when these figures are changing, right? Okay, hope this Beer-Lambert law will be okay. So there can be several, complicated questions with this. Be careful. Try to do your, activities in the book, right? So, පොතේ තියෙන ඒවාම තමයි, not the activities, your knowledge from the book will be evaluated, right? So make sure you have understood everything. Okay, so these are the answers. You are correct, right? Okay, now this is again macroscopic view. Which intensity out of I1 and I2 is bigger if epsilon 1 is greater than epsilon 2? This is greater than epsilon 2.
I2 is greater than I1.
Epsilon
Epsilon.
1 is greater than epsilon 2. So which of these I1 the I2 the?
I1.
Give me the relationship.
No, I2.
I2 will be big.
I2 is bigger. I2 is
I2
bigger because
greater
of
than I1.
epsilon 2 is less, no?
When
Uh,
epsilon 1 is greater, the absorption will be greater. So I2 is greater than I1.
Correct? Is that the correct answer? So if epsilon 1 is greater, right? So you can apply A is equal epsilon CL. If this is greater, what will happen? Absorbance is high. That means here more absorb, right? Then what will happen? The beam coming out is less. Clear? Compare to I2. Is that the answer you have given?
Yes, ma'am.
Yes.
Right. Okay. So I1 should be less than I2. Right. Okay. So hence the mole extinction coefficient, epsilon, is a measure of ability of molecule to absorb. If this is high, if epsilon is high, the ability of absorption or ability of the molecule to absorb radiation is high. That means the mole extinction coefficient or the epsilon value will give you a measure of ability of molecule to absorb radiation. Right? Clear? Okay, that's why epsilon is depend only on the frequency. Right? If temperature constant and concentrate, if the and the other issue is epsilon, it's depend on molecule to molecule. Suppose for KMNO4 molecule, the epsilon is different to another let's see, it's ethanol molecule, right? So ethanol solution, right? So epsilon is depend on the solution or the molecule and also the frequency. Okay. Right. So now we are still in the macroscopic. For a given chemical species, that's why we make it a given chemical species. Chemical species change and epsilon also changing. Right? If the chemical species for a given one, epsilon depend on the frequency. If temperature is also constant, epsilon is depend only on the frequency of electromagnetic radiation. Right? So that means the absorbance versus frequency, right? So in a spectrum, so this is a spectrum, right? So that's how in spectroscopy, we are going to study using the spectrum, right? So this is a spectrum, right? So why you can observe these, the peaks, different peaks. Why? What is the reason? That is because the absorbance versus frequency is called a spectrum and it is spiky in nature. You can observe different peaks. Spiky nature of a spectrum can be explained by using the spectrum, this type of spectrum. That means different frequencies, you have different absorption, right? So that is how it's spiky nature in your spectrum, right? I'll further explain it when you go down. Okay, so now close your eyes and imagine now you have a matter, right? So go inside the matter and you are sending a beam of light into this matter, right? So this beam can consist of particles, right? So what will happen? So you have molecules in this matter, right? So what will happen? These molecules, we'll see it's molecular particles, right? Like this. There can be molecules like this. So once these, the photons, the particles coming from the beam, that means green color one, if they hit the molecule that certain energy can absorb by your molecule and the remaining can going out, right? So the photons may collide with your molecule during the passage through matter, right? So the energy exchange may take place. So what will happen when these molecules, when they passage through the matter, it can collide with these molecules. The H nu can collide with these molecules, right? So these can be collide each other. Okay, so during this collision, what will happen? Huh? Certain other energy can decrease, well, passage. So the certain other energy can evolve, right? So during this exchange may take place such collisions, right? So that's how it is important to study the interaction, right? So you are now in the microscopic view. So now can you understand what is the macroscopic and microscopic view? So imagine you close your eyes and slowly go into the matter. So you have molecules. Initially you have, it can be a compound. Let's see, it's a salt piece of, a salt, right? Then you go inside, you have sodium chloride molecules, right? And you have atoms. And likewise, inside the matter, you have molecules, right? So you go down towards matter. And when you hit a beam of light into that matter, your molecules can interact with the photons, that means particles in the electromagnetic radiation. They can evolve some other radiation from that, right? So in absorption of radiation, so there can be absorption taking place in between collisions. That collides with a molecule, disappears with transfer of its energy to the molecule, right? So what will happen? During that collision with the molecule, it can disappear, transferring energy to molecules. And let's see very quickly a small video how it happens. Give me 1 second until I will get this. One second. I need this is not what I want really. Sure whether I can get it. Okay. Right. This is, yes, this is the one. Okay. Can you everyone hear this?
No, madam.
No?
Can't hear, madam.
Can't hear? Okay. Sorry.
No, madam.
Wait 1 minute. I should. Hope now you can hear this.
This.
See.
So instead of being a rainbow of light, we're going to get these discrete units of
Yes,
light,
madam.
these
Yes,
discrete
madam.
photons that are carrying discrete amounts of energy. And this was puzzling to scientists for a long time. We could also shine light through that discharge chamber and parts of it would be absorbed. And so this would be the absorption spectra. So
Discharge
most of the light would
chamber.
make through, but some of it isn't going to make it through. And this
May-
puzzled scientists for a long time until
this is
Niels Bohr
hydrogen.
finally figured it out. And what's happening if we look at a hydrogen just in the first two energy levels
Bohr
is that
model,
as
right?
the electron goes around the atom, as
So
it jumps to a
your
lower energy
electron
level,
Can
it's
go
going to give
the
off a
ground
photon
level,
of light. And for it to
and
move
that
up to that
hydrogen,
other energy or
when
that
it
higher
comes
energy level, it's
to
going to
this
have to
higher
absorb
level,
a photon.
absorb
And so there are
emit.
discrete colors of light that are required for it to jump up. And as it jumps down, it's going to release these discrete colors of light as well. If you hit it with other colors, it's not going to do anything. It doesn't have the right amount of energy. And so this is conservation of energy. Conservation of energy in an atom or in a nuclei when it absorbs a photon. So we call that absorption. And so what does that mean? The amount of energy in the photon and the atom or nuclei before absorption is equal to the amount of energy inside the atom or nuclei after absorption. And same thing applies with emission. And so as we give off that photon, energy is conserved. The amount of energy we had in the atom or the nuclei before is equal to both the photon and atom or nuclei after. Now this is really valuable in science because we could look at what's being given off, so we can look at the spectra of emissions from any kind of element or molecule, and it tells us what elements are.
Yes. So spectrum, the beam coming out or the emission or spectrum, it's important to study what type of element is that.
Going to be found inside it if we know what those energy levels are. And so if you know anything about visible light, it's all the colors of the spectrum. So as we shine it in a prism, as it moves through the glass, different wavelengths of light are going to travel at different speeds, and so it's going to split it into this spectrum. Now know this, that on the red side there's a part of the spectrum that we can't see, that's infrared light, and there's going to be UV light on the other side, and we're just seeing that.
Here you have here this part. What do you have here? Huh? This end you have IR and this side you have UV light, right? Most of the blue color range you have UV and this is the visible. This range is the visible range and this is IR and UV.
A part of the spectrum that we can't see, that's infrared light, and there's going to be UV light on the other side, and we're just seeing that visible spectrum that's going to be right in the middle. And so if we look at those energy level diagrams, for example, in a hydrogen atom, if we were to hit it with the right color of photon, so let's shine on it the right color of photon, let's say a red photon, watch what happens when it hits that electron. It jumps to a higher energy level. Now let's say it falls down to a lower energy level. What kind of color is going to be given off from that electron? It's going to be that red photon again. But what happens if we hit it with a green photon, for example, and it doesn't have the right color, doesn't have the right energy? It's never going to be able to move. Let's say we hit it with a...
Yeah, see now the green light is hitting this electron. Can it be excited? Huh? No,
No,
that means only the red can. Yes, only the red color can absorb and it goes to the higher level. So let's see again.
Yellow photon, what does it do? Again, nothing. And so these atoms are being bombarded by different colors of photons, but it has to be the right color. Let's say it's the right purple color. What's going to happen? It's going to jump to a higher...
So once the purple color, because it has higher energy, purple side, UV side, right? It can go to the, when it bombard, this atom is bombarded with UV range, that means blue color range, it can go to a higher level, right?
energy level. what happens as it falls down to that ground state, it's going to give off that same exact photon. So you can model this. This is a PHET simulation. What I'm going to do is take one hydrogen atom, put it in a discharge chamber. I'm going to use a cathode ray to hit it with an electron and watch what happens. It gets high energy, and as it falls back down, it gives off a certain color of photon. Now, if I were to hit it with not just one electron, but a continuous stream of electrons, before it's able to fall down again, it's giving off different colors of photons. So we're getting all these different colors of photons, and you can see on the spectrum on the bottom of this page, it's kind of plotting what color those photons are. So now let's do multiple atoms. Let's do a bunch of atoms. We're going to hit those with a continuous stream. And so what's happening is they're all at different energy levels. And so if we were to plot the average of all of those photons that are being given off, that's going to be that.
Have you noticed these intensities, how it increases? The number of atoms increases. You can increase the spectrum, hydrogen spectrums, the intensity of a given peak, right?
Purple color we get. But if you were to do a spectrogram on it, you could see on the bottom that we're getting those bars. Now, way to the right, we've got the infrared. Way to the left is the UV. But you can see those 4 spectral bars that I just talked about a second ago. Now, let's say it's not hydrogen in the middle. So this is going to be a hydrogen spectrum here. I've sped up the simulation.
So have you seen the hydrogen spectrum simulation here? Electrons are moving up, but these intensities, it cannot go to higher level because the energy difference is very high, right? So up the stimulation, you can getting those bars, but let's say change
So we're
it
getting
to
those
mercury.
bars. But let's say we change it to mercury. What are we going to get? Totally different electron, totally different energy levels. And so we're going to get different color. This is what sodium would look like. This is what neon would look like. And so when you look at a neon light and it gives that reddish color, it's the sum of all those different photons that are being given off from that neon gas. Electron or...
Right? So that's how it's really important to learn all these things. Right? So by looking at the spectrum, you will be able to investigate what sort of molecule is that. So the hydrogen, whether it's hydrogen atom, whether it's a neon atom or mercury atom, right? So likewise, even the molecular spectroscopy can also be used to determine its structure, right? So that's why it is important to study the IR spectroscopy, UV visible spectroscopy, microwave spectroscopies, right? So here in this study, we are studying the UV visible as well as microwave spectroscopy in your 7th session, right? 7th one, microwave. Okay, so now what will happen? We are now in the microscopic view. So we are inside you go into the molecule and here you have 2 energy levels within the molecule, right? So these are the 2 levels, E0 and E1, right? So what will happen when H nu, the photon energy hit this electron, it can goes up in the molecule, right? So it goes to the excited level, right? And we call this as absorption, right? So now what will happen if this is going down to the ground level? This phenomenon is called emission, right? Absorption spectrum and emission spectrum. So by looking at this spectrum, you will be able to analyze what sort of molecule is that. So for example, carotenoid molecules has this type of spectrum, right? So it gives the absorption. What sort of color is that? It's red to orange range. That means it's absorbed the visible region, right? So why are all these shoulders in their spectrum? That is because your carotenoid molecule, you have different vibrational levels within the carotenoid molecule, right? So when this electronic excitation takes place, there can be vibrational changes as well. So, I mean, by looking at this spectrum, we will be able to say what sort of energy transitions can take place inside this, right? So that's why it's really interesting to study all these spectroscopy. Clear? Okay, so now this is absorption and the other side is emission, right? So which one is correct here? Tell me which is the correct answer?
Third one.
Any other answers? Huh? Which
Third
answer
one.
is correct here?
Third one.
Third one.
Third one. Why third one? You have to give exactly this difference. E naught minus E1 minus E1 difference. Exactly. Only if this H name lies in between these difference, the energy difference only your molecule can absorb. Right? That is H nu should equal to exactly this difference. If this is another color, suppose it's green color light, no, this cannot absorb as this is not fulfilled. So exactly E1 minus E0 should be given, right? So this is the correct answer, not the higher or the lower energy level, right? So this phenomenon is called the conservation of energy, right? So what is conservation of energy? That means you have to provide for the absorption the exact amount of the energy difference, E1 minus E0. That is called the conservation of energy, right? Conservation of energy is called that lead to the Bohr condition, right? That means only if this frequency lies between this difference can only absorb. Otherwise, your molecule cannot absorb. Clear? Is it clear?
Yes, madam.
Okay. So now, can you now explain why the absorption spectrum is spiky? Now, it should be very clear to you. Now, why the spiky nature of your molecule? What is the reason of having these type of peaks in our spectrum? Or it can be these type of peaks. Why is that? Huh? Huh? Why? What is the reason?
Molecular
That
observes the specific frequency
Yes,
radiation.
that means only if the conservation of energy, only the difference can only absorb the exact frequency, the green color frequency can only absorb, not the red and blue. Clear
Yes, ma'am.
හැමෝටම clear these
Yes,
concepts
madam.
very clearly put them into your mind, right? ඔළුවට හොඳට දාගන්න. Then only you can understand the advanced stuff. හැමෝටම clear Clear නැති
Yes,
කෙනෙක්
ma'am.
ඉන්නවා නම් please kindly ask me now itself. Spectroscopy, it's not hard. කවුරුත් seniors ලා කිව්වට now you all can count argue. No, it's not a hard subject, right? You should be able to teach the others as well. Once you get the concept, exact concept into your mind. හරි? මේක අමාරු නෑ. කවුරු කිව්වත් කියන්න no, this is not hard. ඒ level එකට ඔයගොල්ලෝ හදා ගන්න ඕනි your knowledge, right? Okay. Now, only this can absorb or giving you the peak, right? So that is why the spiky nature of spectrum, right? Okay, so now we have given a molecule having two energy levels. One is E1 and the other one is E2. E1 is equal to this much of energy. E2 is this much of energy. So now I'm asking which photons will get absorbed by the molecule? මේ හතරෙන් which photon can give you a beam of radiation having photons, which gives you a absorption.
0.5,
Second one.
0.5 into 10 to the power minus 21.
Any other answers? කොයි එකද absorb කරන්නේ?
0.5 into 10 to the minus.
0.5 because of the energy difference is 0.5.
All agreed?
Yes, ma'am.
Others? ඔය නිදි කට්ටිය? කොබන හරින්න?
Yes, ma'am.
Why? So what is the difference between these two? 0.5 10 to the power minus 21. So this only can absorb, not these photons. Clear? Is it clear? Right. Okay. So this one will only be absorbed by your molecule. Your molecule have two energy levels. It is given that these are the two energy levels, right? Okay, so now only one photon can absorb by this particular molecule. Okay, so now activity 2. Suppose you have 4 energy levels. Quickly take a piece of paper and draw it in your paper. You have 4 energy levels. E1, ඉක්මනට label කරගන්න. E2, E3, E4. These are the energy levels. So I'm asking, what is the maximum number of absorption lines that can be in the absorption spectrum? So a spectrum is given here. මං අහන්නේ, how many number of absorption peaks? මේ වගේ peak කීයක් පේනවද?
6, 5, 6.
Six. E1 to E2
How
1
many?
and
6.
E1 to E2 1.
Any other
E1
answers?
to E3 2. E1 to E4 3.
Any
E2 to
other
E3.
answers?
Yes, 6.
Oh, අනිත් අය. 3.
3.
Okay. We have 2 answers. 3, 6. Any other answers? කොබලන්න මේ නිදන් ඉන්න අය. නම කියලා කතා කරන්න ඕනේ. අචිනි. How many number of maximum
Six.
peak?
6.
6. Okay. 6 හරි තියෙනවා. හන්සනි. අකිලා. සනුෂ්ක.
3, ma'am.
Okay, 3. Sanushka. How many maximum number of peaks? Huh? Yoshan. Yoshan, how many number of maximum peaks?
3.
3. 3 or 6? Answers දෙකයි. Any other answers? Kavindya. Right? So let's see. So what
7.
will happen? 7. 7 තියනවලු. Right. So let's see. You have only 4 energy levels. So these are the energy levels. Right. So how can you get the absorption? So starting from the ground level, I'm asking just the maximum number of absorption lines. Starting from the ground level, you can go up to the first excited, second excited, and third excited. Right? And again, starting from the second excited, you can go E3 to E4. And another line can appear from here to here. So now altogether, how many?
5.
3 plus 2
Six.
plus 1?
6.
6 maximum peaks can observe. Right? So indicate the frequencies of these lines in absorption spectrum. So where you can appear these lines. So what is the difference, energy difference here? From here to here. So what can be the frequency? Let's take it mu1. From here to here, the energy difference is this much. mu2. Right? So this is your mu1 line and this is mu2. And likewise, you can have three maximum peaks where you can have mu1, mu2, mu3 to mu6. Right? Is that clear? Clear
Yes,
the?
ma'am.
ඔය අනිත් answers දීපු අයට clearද?
Madam, can you explain again?
Yes. Now here I'll go come down and see. Okay, so now these are the 4 energy levels, right? So you have E1, E2, E3, E4. So these are the possible transitions. Is it clear?
Yes, madam.
1, 2, 3, 4, 5, 6. If you have 4 different energy levels, you can have 6 possible maximum lines, right? So now what is mu1 is equal exactly the conservation of energy. E2 minus E1 over H. mu2 is equal E3 minus E1 over H, right? So likewise, you have 6 different frequencies, right? Clear the? Is it clear now?
Yes, madam.
Yes, madam.
Okay. Right. So now let's move down further. Okay. So what is a spectrum? Why a spectrum is spiky? So energy of a molecule is quantized. It's not a range of energy. It's not a concrete energy level. It's quantized. The quantization of energy. A molecule can have only certain set of energies, right? That is called hence the energy level difference is also quantized. Since the energy is quantized, the difference is also quantized. Only this packet of energy. So this consists this packet of energy, right? And according to the Bohr condition, the conservation of energy, only a photon, those energy is equal to this difference, right? Only if you have the energy difference, only this difference can absorb by the molecule. So that is called the conservation of energy, which leads to Bohr condition, right? Right? Okay, so hence only photons belonging to a particular set of frequencies can be absorbed, making a spectrum spiky, right? So that is why you can observe a spiky nature of a spectrum. Okay, so now we are still in the microscopic wave, not all collisions. Suppose here I have mentioned if you have 4 different energy levels, you can have 6 transitions maximum. However, not all these 6 transitions take place. So the collision between a photon and a molecule leads to absorption even Bohr condition satisfied. Even though this Bohr condition, what gives you the Bohr condition again conservation of energy, only this difference can absorb, right? Not only this, there should be another satisfaction. So what is that? We called it as probability of transition, right? Not only the Bohr condition satisfied, also the probability of transition. What is the probability of transition? It depends on the nature of the wave function. That means for a given energy level, you can define this by using a wave function. So we called at certain times Gerard transition, un-Gerard transition. So likewise, we define these each energy level, right? Using the wave function. So depend on the not only the Bohr condition, it should satisfy the probability of transition of the molecule in upper and ground level, right? So that is called the probability of transition, right? So that can gives you the height of a peak in a spectrum depends on the probability, right? So there are certain peaks are having very high height. That means the probability of transition is high, right? So likewise, so this is the rule is indicated whether this probability of transition is 0 or not is called the selection rule, right? So we called it as selection rule. So not only the energies, the conservation of energy or the Bohr condition, your molecule should satisfy the selection rule as well, right? So let's see this activity and try to understand what is selection rule or the probability of transition. So consider the same molecule having 4 energy levels. So what is the maximum transitions? Kiyak tibunada?
6.
You have 6 number of transitions, right? However, this question tells you the probability of transition, the Bohr condition. According to the Bohr condition, it should give you the 6 lines. However, the selection rule or the probability of transition gives you in the absorption spectrum delta n is equal plus 1. So what is that? Delta n is the n1 first excited ground level, n2 first excited, likewise n1, n2, n3, n4, right? Delta n plus 1 means your molecule electrons can go from here to here, from here to here, right? From here to here. Can it go from here to here?
No, the delta n is then plus 2.
Plus 2. It's
Oh.
not the selection rule. According to the selection rule, it cannot go from here to here too. Right? So these transitions are prohibited or forbidden transitions. We called it as forbidden transition according to the selection rule. These are allowed transitions, right? So These are only the allowed transitions. Suppose this delta n is given as plus or minus 1, then what will be the other case? It can also this one, the emission, that is emission. Is it clear now? These also allow transitions, right? However, this gives you only a delta n plus 1. So now what is the maximum number of lines according to this selection rule?
3.
Very good. Only 3 transitions can take place according to the selection rule. So even though you have 6 lines, the maximum 6 line obeys according to the Bohr condition, right? The conservation of energy. Bohr condition anuva, you have 6 lines. However, you can have only 3 lines because of the given selection rule, right? So these are the only possible lines. Clear the, so you can observe only 3 lines in the absorption spectrum, right? Is it clear? Haridha?
Yes, madam.
Yes, madam.
Okay, so now quickly, what's the time?
250.
Almost 2 hours, ne? Okay, quickly. We will move quickly. Give me 1 second. You have the schools from 1 to 3 and again 3:30 to 5:30, no? Huh? So according to the master timetable, you have 2 time slots now? Huh? Hurry up quickly. No, I'm not going to do such long time. Mga hanne. Huh?
In the
Because-
email, it was not mentioned.
The master timetable from 3:30 to 5:30 also we have, madam.
Yes, that's what I'm asking, right? So, Dr. Kumudika will continue with the, after my phase equilibria, Dr. Kumudika will continue with the electro, right? So that's what I'm asking. I want to hand over the session to her, no? Right? So I will have another phase equilibria as well, right? So quickly we'll do it. Okay, so these are the 3 possible lines, right? So now let's see. This is a person. Suppose this is a molecule, right? So what sort of molecule does this person is having? When he's on a mountain, what sort of energies that he does have? He can have potential energy and kinetics energy, right? So those are the 2 energies. So likewise, your molecules can have 5 different types of energies, right? It can be translational, rotational, right? So these atoms combine with 2 bonds, right? So 2 atoms can be joined with a bond. So what will happen? They can rotate, right? So in between the axis, and it can be rotate the stretching and bending frequencies, right? So what is stretching? Huh? What is stretching? When the bond is, 2 atoms are joined each other using a bond, so it can stretch, right? So it can rotate in between the axis, right? So these are the rotational energies, can rotate, the molecules can rotate. So there can be vibration, stretching vibrations and bending vibrations, right? And there can be electronic energies, due to the electronic, the nuclear within the electrons. And there can be nuclear energies because you have nucleus and electrons are moving in the what we call the orbit, right? So these are the electronic energies, and within the nucleus you can have nuclear. So these are the types of energies can a molecule have, right? Okay, so now there are different types of energies are quantized separately, right? So likewise, your molecule can have different types of energies. So what is the highest of those? Electronic. The molecule can have electrons moving in a orbital, right? So this electronic energy has the highest difference, right? So that is called the electronic energy. And for a given electronic level, you can have vibrational energies, energy levels. And so these are the vibrational energy. So for a given electronic energy, you have V0, vibrational level 1, V is equal 1, vibrational level 1, 2, 3, likewise, right? So these are the electronic energy levels, E0 and E1. For E0, this is E1, right? So for a given electronic energy, you have vibrational energy. So for given E1, you have V1, V0, V1, 2, 3, likewise. Clear? And the energy difference between rotational levels, these are for a given vibrational level, you can have several rotational energy levels, right? So that's how the energy of a molecule can have different uh, energies quantized each other, right? So these are the rotational. So what is the rotational? This is R1, 0, R1, R2, likewise. Clear? Is it clear? So now when this electron is moving from R1 to R2, you have to provide only this much of energy, right? And if you want to make a vibrational transition, then you have to provide this much of energy. So for an electronic transition, you have to provide this much, right? So that's what these energies are separately quantized. Therefore, you can observe different spectroscopies. Is that clear? So can you all remember, I have told you this has the highest electronic transition. And next is the vibrational energy transition. And this is the rotational energy transition, right? So this gives you the highest energy transition. So where you can observe the spectrum. Can you all remember the electromagnetic radiation? You have UV visible, and you have what else? IR, and here
X-rays.
Samnathibune. This has to be changed.
X-ray.
X-rays and gamma.
You have IR here and UV, high energy, and X-rays, gamma rays, and here this side,
Radio.
microwave, right? And radio, right? So now, see, the difference is higher here. So this occurs, which range? UV and visible range, right? So that's why the electronic transition occurs in UV visible range. which leads to UV visible spectroscopy. Electronic transitions වෙනවා that leads to UV visible spectroscopy. So here the vibrational transition that occurs in the IR region. So that's what in the IR spectrum you can observe your stretching, bending transitions, right? Likewise. So you see a vibrational spectrum. By looking at the spectrum, you will be able to study its vibrational peaks, right? And this is the lowest. Rotational is the lowest, where it observes in the microwave region. So in your session 7, right? So you are going to study the microwave spectroscopy. Clear? And
Yes,
IR
madam.
spectroscopy. This is IR spectroscopy and this is UV visible spectroscopy. So that's why you can study several types of spectroscopies and obtain the spectrum, and hence you can study its molecular behavior, right? The structure can be elucidated, right? So that's how it's really interesting. Huh? Isn't it interesting to study all these spectroscopies?
Yes, madam.
Yes, ma'am.
Yes, right? So let's move very quickly. So this is how the electronic energy difference is the highest, which occurs in the UV visible, and the vibrational next occurs in the IR, right? So this occurs UV visible and this occurs IR. This occurs microwave spectroscopy, right? So all depends on the photons. So photons having very different amount of energies are required in changing electronic, vibrational, rotational energies of a molecule, right? Hence, different types of spectroscopies. What are the different types of spectroscopies? Involve radiation in different regions of microwave, electromagnetic radiation, right? So what are the different types? Rotational now, microwave, vibrational, it's IR, electronic, it's UV. Is it clear? Now, these are the 3 different types of spectroscopies that we are going to study. Clear? Is it clear for everyone?
Yes, madam.
Yes.
Okay, madam.
Madam, can you tell it again? Rotational.
Yes. Then Mehemani, Gayani, now you have different in a molecule එකක් ගත්තොත් you have different set of energies separately quantized. Vibrational has the highest energy difference. So for a given monkey vibrational the
It's electron.
electronic.
The biggest.
Electronic has the biggest. For a given electronic, you can have several vibrational. මේ දෙන ලද එකකට vibrational තියෙනවා. For a given vibrational, you can have several rotational. Right? And this difference is the lowest. ඒක appear වෙන්නේ microwave region එකේ. Why? You have to provide only this much of energy. Right? For a vibrational, you have to provide this much of energy difference. So that appears in the IR region. Right? So this is the highest electronic. So which appears in the UV visible. Clear the?
Oh, madam.
That another guy.
Yes,
Madam,
madam,
can you-
got it. Thank you, madam.
Okay. So තව මොනවද තියෙනවද ප්‍රශ්න? Any other questions? හැමෝටම තේරුණාද? This is very important to study all these
Madam, can you repeat it
Madam,
again,
what
please?
about the X-rays and gamma rays?
Yes, X-rays and gamma rays, we are not going to do it in this level, right? So, however, when you come to the special degree, right? So, this time, there are 20 number of special students we have in our department, the chemistry, right? So, they did well. So, that's why this is the huge, the largest batch we have for special in chemistry, right? So, you have to be, I mean, even next will be your set, right? Yeah. So you also can do this, right? So try to get A plus grade for organic, physical, as well as inorganic theory part, right? And also the practical. Sham, now is it clear to you now? The lowest energy appears the rotational. Here, according to
Okay,
this,
madam.
which is the lowest. This difference is the lowest. Right? So this is the lowest difference. Energy difference is, so which lies in the microwave. Right? So this is next lowest. Which appears in the IR range. Why? In your microwave electromagnetic radiation, you have UV visible and then IR and
Microwave.
microwave. Right? So මේ පැත්තට යනකොට එනර්ජි මොකද වෙන්නේ?
අඩු
Huh?
වෙනවා.
අඩු වෙනවා. Right? Energy අඩු වෙනවා means you have to provide the lowest energy for microwave. And when it comes to this IR, little higher energy than this. And when it comes to the electronic, this much of difference, which lies in the UV range. Is it clear now? Sham?
Oh, yes, madam. Yes. Thank you, madam.
Okay. Hope now everyone clears this part very well, right? So now with this basic concept, you should go through your books. So by today night, I can upload your all course materials into this. I will email it, right? So the link, Google Drive link, Google Drive dala, I will upload it into.
Please excuse me, madam. Can you upload?
Sorry, Gaini, I can't hear you.
Can you upload this presentation as well, madam?
Yes, I will upload this as well, right? So the recording එක ඇතිනේ? Huh? Recording also I can upload the recording. Why do you need the
Madam.
presentation as well?
Yes,
Yeah,
madam.
madam.
everything
It's
is
good,
done?
madam. No,
Yes,
madam.
madam.
Sometimes recording, if we are unable to listen it again, it will be helpful for us to have presentation.
Okay, let's see. Right? Okay. So Sham, what did you ask?
No, madam. It's clear to now, madam.
Okay, right. So now the theoretical study of spectroscopy is involved the frequency of line. That means whether it's nu1, nu2, likewise. And the selection role. So you know whether the probability of transition giving you the selection rules. Whether it's so certain cases, Gerard to Gerard. One wave functions for a given molecule, Gerard to Gerard transition is forbidden. However, Gerard to ungerard is ungerard. These terminologies you might get when you read a textbooks, right? So the wave functions can be defined Gerard, ungerard, likewise. So these can be allowed transitions. So the selection rule is the one which you need this. So the peak height, peak width, right? And peak width is also different. This is the peak width, right? So these are the theories that you can study here. Right. Okay. Now that's all about the spectroscopy. Okay. So these are the summary. I'm not going to go into details again. Right. Go condition and selection rule and probability of transition. You should know all these things. Okay. So now hope you have developed your broad view of the spectroscopy, right? So the aim of this compulsory day school is to give you the broad view of the spectroscopy, not only the spectroscopy, all the other four units, other 3 units, right? So then only with that view, broad view, you will be able to go specific spectroscopy, right? And underlying microscopic processes that creates the spectra. Okay. So that's all about the spectroscopy part. So let me, without any break, shall I continue with the this thing? Huh? I don't think you want a break. Do you need a break? ඔයගලන්ට break එක ඕනේ මටනේ. මමනේ කෑ ගැහුවේ නේ. Huh?
Yes, sir.
Huh?
No,
Do you
ma'am.
need a break?
Give a
Hopefully
small
no.
break,
We can
madam.
continue.
Huh? Small break?
Yes, madam.
Yes,
Yes?
madam.
Why?
We need to pray, madam.
Sorry, I didn't get it.
We have to make our prayers.
Then at what time? Now it's 3:10 now. Huh?
A 10 minutes break is enough.
No, then we need to do the electrochemistry part as well now. So shall I continue with this, and in between electrochemistry, we can give you a break. Is that okay?
Yes, ma'am, it's okay.
Huh? Others? Hurry up.
Okay,
Did you
ma'am.
tell me?
Yes,
We
madam.
can continue.
Okay, madam.
Yeah, better continue.
Yes, ma'am.
Otherwise, even spectroscopy, sorry, electrochemistry is also there now. In between those two, you can get a break, right? You can come back after 5 minutes. Who told me that you wanted to pray?
Okay, madam.
Okay, you take your own break. It doesn't matter. It's just simple part you have to do here, right? The initial part you can understand. Okay, so now the phase equilibria, right? So this is again really important. The phase equilibria. Why? So studying about the phase transitions and the what will happen inside the phase. So it is really important to study this, right? So let's see, this is your unit 4, the phase equilibrium, right? And this covers the phase equilibrium is basically a map. Phase diagram is basically a map, right? So it is something like this, right? So this is a phase diagram for water, one component system. So only water is there. So suppose you have a glass of water and into that you are adding an ice cube, right? Cube of ice. So what will happen? You have a solid here and you have liquid here, right? So however, in this system, what is the component you have? How many components? You have only water as the component. So number of component here is 1. Is it clear?
2 components.
No, I'm asking what is the component here?
Water.
H2O.
Water.
You have only water here. So what are how many number of phases? You have
Two phases.
solid phase here in
Solid
I,
and liquid.
solid and liquid. This is solid and this is the liquid phase, right? So two phases are there. P is equal to and C is equal 1. So phase diagram is basically a map, something like this. So this is the phase diagram for water. So that gives you this type of behavior, right? So it's depend on temperature versus pressure diagram එක ගත්තොත්. So this is for a one component system. So what is the component here? Water, right? This is the phase diagram. So you have 3 domains here. What are those 3 domains? Solid domain, liquid domain, and gaseous one. In between, you have limits of stability. These are the limits of stability, right? From here to here, what will happen? Solid liquid equilibria, right? From here to here. So what is the equilibria? Solid to
Gas. Water
gas.
vapor.
Yeah. From here to here, solid to
Liquid.
liquid equilibria. From here to here,
Liquid to water vapor. Gas.
liquid to gas equilibria, right? So these are the limits of stability, right? So let's see what will happen. Right. So now your pressure is somewhere here. So now you are going to increase the temperature slowly of that solid. So somewhere here you have only the solid. Mary, I say. So you are slowly increasing the temperature. So at this point, what will happen? Your first liquid water particle appear. So keeping the pressure constant at constant pressure, when you increase the temperature, the solid will melt, right? මොකද වෙන්නේ? ටික ටික your ice cube is dissolving, right? Slowly dissolving. And temperature is going down, right? And now what will happen? Again, you are going increasing temperature from here to here, keeping pressure constant. The first vapor particle appear. So thereafter, you have only vapor, right? And also, similar way, take gaseous, the water vapor, right? Here you are having water vapor. So keeping the temperature constant, increasing the pressure. So at this point, the first liquid water particle appear. So after that, you have all liquid, right? So likewise, in between these lines, those are called the limits of stability. How many number of phases you have
3.
on top of these lines?
2 phases.
2 phases. In these domain, how many phases you have?
Only solid one.
Only solid. How many components you have here?
One component.
This is one component system. This whole thing is only water. So C is equal 1 all the time. So here you have 1 phases. P is also 1. So how many phases on top of this line? Me line එක උඩ?
2 phases are there.
2
Solid
phases.
and-
What are those 2 phases? Solid and
Solid and
gas
gas.
phase. On top of this line,
Solid and
you
liquid.
have
2 phases.
solid and liquid. 2 phases. On top of this line, Again,
Liquid and gas,
two
two phases.
phases are there, right? So here you have P is equal to. However, all these domains you have number of phases 1, right? Is that clear? Okay.
Yes,
So
ma'am.
now in what is this point? මෙන්න මේ point එකට අපි මොකද්ද කියන්නේ? We call this point as triple point. Why it's a triple point? All solid, liquid and gases are in one equilibrium. Right? මේ point එකේ තුනම එකට equilibrium එකේ තියෙනවා. We called it as triple point. So solid, liquid, vapor. All three are in one equilibrium. So how many phases are there at the triple point?
Three phases.
3 phases. You have P
Solid.
here 3, right? So how many components?
Only one. Water is
Only one. Only water is there, right? So this is called the triple point. Is it clear now? So you should
ma'am.
be now able to explain why you go up country, right? So when the temperature drop, what will happen? The water boil when temperature එක කීයද? Huh? What is which temperature at which the water boil?
100.
100
No,
වලට වඩා 100 වෙනවද?
will increase.
Decreases.
100. If it is 100, that means your pressure is
Right.
1 atm. At 1
1
atm, 100 degrees. The boiling point of water, right? So if it is dropping, coming down at hill up countries, water boils at lower temperature. What is the boiling point? Liquid to gas point. That at this point, temperature, sorry, pressure, when it is, suppose it's 1 atm is here, right? So from liquid to vapor, from here to here, at this point, first vapor droplet is appears. 1 atm, that means this is 100 degrees temperature, right? However, at lower pressure, when we go to Nuwara, the pressure drops. You are starting somewhere here, right? So what will happen? Your water boils at this temperature. It should be lower than 100. Is it clear?
Before 100.
Below 100. Clear the?
Yes,
Is it clear? Okay. So now that's how you, by looking at the phase diagram, you should be able to basically, it's a map. Ekai මං කිව්වේ it's a map of phases, right? Okay. So when we move down, so these are the terms that we are going to use in the phase. System, equilibrium, right? So what is a system? System is an assemble of materials that is isolated in some manner from the rest of the universe, right? So you have here the your rest of the universe, you have a liquid, right? So other than the universe, here the material isolated from the other, right, is called the system. And equilibrium is the lowest energy state of a system. System ekaka lowest energy gives you, which is no tendency for a spontaneous change, right? If the change is spontaneous, that means what is its delta G? If it is happening spontaneously,
Delta G minus.
it should be a negative value, right? Delta G negative nang thamai, the reaction is spontaneous, right? So for equilibrium, the lowest energy state in which there is no tendency to spontaneous equilibrium change, right? So for example, homogeneous chemical equilibrium. So now Here you have gas, gas, gas. It's homogeneous, all inside a gas system. However, it's a chemical equilibrium. Why? A chemical reaction is taking place. Nitrogen and hydrogen collectively forms ammonia. It's a chemical reaction. And this is heterogeneous chemical layer. Why? You have solid here, however, gas here. Right? So that is heterogeneous. However, again a chemical reaction taking place. And this is a heterogeneous physical equilibrium. Solid to liquid. What is called? Melting. That's just chemical physical equilibrium. Not a chemical reaction taking place. Right? And vaporization and sublimation. So what is sublimation? Solid to vapor transition. Right? Is it clear?
Yes,
Yes,
ma'am.
ma'am.
Okay. Okay, up to now, I hope everyone clear? Right. So we'll quickly move. Right? Okay. So now let's move down. Okay. So now the phase rule. What is phase rule? The Gibbs phase rule we called it as. So this is an important tool used for the quantitative treatment of systems in equilibrium. When a system is in equilibrium, quantitatively you can define the system by using the phase rule. So that enables you to predict the condition. So whether your system, how many number of phases, how many number of degrees of freedom you can express by using the phase rule, right? And there are more different phases are present in equilibrium form a heterogeneous. The number of phases are different, it's heterogeneous. However, this rule predicts qualitatively the effect of temperature, pressure, and concentration. So phase rule may predicts the qualitatively how these variations occur, right? So let's move down quickly. Right. Okay. So now let's see. Okay, now this is the phase rule. So what is phase rule? F is equal C minus P plus 2. Right? So what is this C? Number of components. What is this P? Number of phases. What is F? Number of degrees of freedom. Right? Clear the? Right. So where these three variables are related to this equation, right? This is called the phase rule. Same, right? Metan F plus F P plus F equals C plus 2 is equal to F equals C minus P plus 2 tamai. So this F is the degrees of freedom represent the environmental condition, right? So here, the previous case, what are the two environmental conditions that we consider? Temperature and pressure. Right? So these are the two conditions for the one component phase diagram for water. So degrees of freedom. So where we can calculate these degrees of freedom. So here, how many number of phases? P.
3.
Mithana?
1.
Only one. One
Only
phase.
one. How many number of components here?
One.
One.
One. Why one component system? So F is equal, C is 1, P is 1 plus 2. Here the F is equal to. So what are those two variables? Pressure and temperature. So this point can be defined by using these environmental conditions, pressure and temperature. These are the 2 degrees of freedom. You can define this point. Now let's come to this point. This point. How many number of phases?
2.
Huh? 2.
2.
How many number of components?
Only one.
1.
Only 1. Right? So what is F? 1 minus 2 plus 2. Here the
1.
1. So that means this particular point can be defined by using one of these variables. Keeping temperature constant තියාගෙන, we can define this point by using only the pressure. Right? And or other way, keeping pressure constant can define this point by using temperature. Right? Clear the? And this point, let's move on to this point. So this, how many number of phases here? Huh? 3 phases. How many number of components?
1.
So what is F?
4.
F kiyada?
0.
Component 1 minus 3 plus 2.
0.
0. That means you don't want any variables, any of these variables to define this triple point. You have the degrees of freedom. Here it's 0. Is it clear, everyone?
Yes.
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 Okay. Right. So let's move quickly. Okay. So the phase. What is a phase? Phase කියලා කියන්නේ a form of a matter which is uniform. Solid phase, liquid phase, gaseous phase throughout the chemical composition. So system containing only one liquid. If there is liquid only, how many phases?
1 phase.
One phase.
Liquid water and water vapor.
2 phases.
2 phases. A system containing liquid water, vapor and solid ice.
3 phases.
3 phases. Here you have pure substance, only solid, made up of one chemical species. Then how many phases?
1 phases.
So solid calcium carbonate is there. How many phases?
1.
You have solid calcium carbonate and solid calcium oxide. How many phases?
1 phase.
1 phase.
කවුද මේ 3 කියන්නේ? right? Okay. Right? So how many phases are there? You have pure substance, pure calcium carbonate and pure calcium oxide. How many phases?
One.
Is it one? No, two phases are there. Why? So solid calcium carbonate is one pure solid and calcium oxide another pure solid. Right? So altogether both are solid phases, differently, separately solidified. So how many phases? Two, right? Clear the
Yes, madam.
separate solidify when separately. Okay. Right. Component එකක් කියන්නේ මොකක්ද? Is defined as the minimum number of independent variable constituents, right? So by means of which the composition of each phase can be expressed in forms of chemical equation, right? For example, this is a one component system. Water having three phases, ice, salt, liquid water and water vapor. So the number of component is 1 here. And sulfur exists in 4 forms. What are those 4 forms? Rhombic, monoclinic, liquid and vapor sulfur. That consists of again 1 because only the constituent is sulfur there. Right? Okay, now degrees of freedom. What is degrees of freedom? It can be the number of environmental conditions which can define minimum number of independent variables. So what are the possible degrees of freedom? Temperature, pressure, environmental conditions, concentration. We are changing the mole fraction. That is concentration. XA. If A and B mix each other, then mole fraction of A, mole fraction of B, right? So which must be fixed in order to define the system completely. Your system can be defined completely by using temperature, pressure, concentration, those variables, right? So by calculating the degrees of freedom, you can have values 1 that is univariant, 2 bivariant, 3 trivariant, and 0 non-variant respectively, right? So these are the degrees of freedom. So consider this equilibrium, all 3 in one equilibrium, solid, liquid, vapor, right? Methune. So 3 phases will be in one equilibrium, only at a particular temperature and pressure. So hence this system does not have at the triple point. What is F?
Zero.
Huh? Zero. That means this is a non-zero variant or non-variant or invariant system, right? So the triple point example. Right. Okay, so now applying the phase rule into each of these systems for a one component system. Water, මං කලින් කියලා දීපු එක, I'm not going to do it again, right? So this is again the phase diagram for water, right? So these are the liquid vapor from here to here, vaporization, right? From here to here, what is this? Sublimation, solid liquid equilibrium. Why? Here, ice solid, liquid water, vapor. From solid to vapor, what is that? Sublimation.
Sublimation.
And this is fusion curve. This is vaporization curve, right? This is sublimation curve. This is the triple point, right? All these I have clearly explained to you all. Right. So now the phase rule. So it is known as vapor pressure curve of water. We have studied this OA curve, right? So this is how it came to univariant system on top of the curve line OA. We have studied this OA line. When you apply the phase rule, we obtain F is equal 1. That means water vapor, its univariant system occurs on top of the line. Right? So now there can be, so far we have studied one component system. Now let's move on to two component system. You have A and B in the system. Right? So in that case, the two component system, if P is equal 1, suppose it's P1.
Madam, excuse me. Hello.
විනාඩියක් ඉන්න දරුවෝ පොඩක් ඉන්න. Yes. What do you want to clarify? Yes.
Madam, මේ මට signal failure එකක් ඇවිල්ලා ඇහුන්නේ නැහැ. මේ madam කිව්වට variant කියලා temperature, pressure අර ඒවා නේද variant වලට එන්නේ divariant ඒ ටික change වෙන එක නේද?
ඔව් change වෙන එක. ඒ කියන්නේ freedom, degrees of freedom කියලා කියන්නේ environmental conditions where you can define the system by using 1 the 0 the 2 the ඒවා. ඒ කියන්නේ depend on that if F is equal 0, it is non-variant, right? That means you don't want any single variables to define the triple point. Clear?
Okay, madam.
Right. Okay, so now we are in two component system, right? Components dekai. So in two component system, assuming that P is equal 1, and now define F. F key है देना. F is equal C. What is C now? C is equal component 2 component na?
2.
So far we have studied only water, right? But now you have two component system. In that case, C is equal to, assuming P 1 කියලා හිතන්න. P is equal 1 plus 2 equals කියා කරවද? F කීයද?
3.
3. That means you need 3 variables to define this two component system. What are those 3 variables? Pressure, temperature,
And
and composition. So now the composition come to the picture. Why? You have mole fraction of A and mole fraction of B. Right? Is that clear? Clear there? So that's why for a two component system, you have to have the phase diagram with 3 variables. Right? So the phase diagram can be represented, then 3 variables තියාගෙන we cannot draw easily the phase diagram, right? 3-dimensional diagram should draw. You should draw a 3D diagram එකක්. Clear the? So is it easy to draw a 3-dimensional diagram?
no.
No. So that what we can do, we are going to draw the phase diagram keeping one of these constant. Pressure constant තියාගෙන we can draw the temperature versus mole fraction. Or we can draw the phase diagram temperature constant keeping pressure versus mole fraction. Right? And also, so these are the conditions. P and T diagram keeping constant concentration. So the third one, concentration, we can draw the phase diagram P versus T keeping C constant. So these are the three possible ways that you can draw the phase diagram. Is it clear? Clear there?
Yes, ma'am.
Yes,
Madam.
madam.
Okay. Right. Okay. So now these are the subunits that you are going to study in this unit 4. Important sections in unit 4. Two component system. We called it as binary system. Two components are binary systems. There can be ideal binary and non-ideal binary. Right? Non-ideal binary systems. Right? So the binary systems can be ideal binary and non-ideal binary. We call this as azeotropic mixtures. Why? It is non-ideal. It's not obeying the Raoult's law. Ideal now, it is obey the Raoult's law. So not only the non-ideal, ideal, there are non-ideal mixtures of liquid, also called the azeotropic mixtures. And distillation of these two mixtures, binary ideal and binary non-ideal, how we can obtain by using the distillation process. And solid liquid equilibria, right? And all these are liquid equilibria, right? Only the liquid is there. Liquid A, you have in a beaker, right? And you add another liquid into this B, right? So now you can make a non-ideal binary mixture or ideal binary mixture. And also there can be solid liquid equilibria. You have solid and liquid equilibria, right? So these are liquid equilibria, right? And also partially miscible, immiscible systems, right? So these are the four main parts of your unit 4. Sorry, 3 main parts. Alright? Terunada. So you can read these very carefully, right? Can try to understand them when I upload the course materials to your email. I will email them. I'm not going to put them in the Telegram group, right? Email karanna separately to everyone. Please check your official emails only. Okay. So ideal binary solutions. So you need to know the mole fraction, Raoult's law and Dalton's law, and temperature, vapor pressure, composition curves, right? Okay, so these are the ideal binary solutions. That means they obey the Raoult's law and Dalton's law, right? So now let's see. You have a liquid composition C1, right? So now tell me, on top of this line, what do you have? Huh? මේ line එක උඩ what do you have? you have only 100% B. Right? All B is there. And however, moving this side, you are adding A to B. So on top of this line, what do you have?
100% of A.
100% A. Right? So, and this side, that means you are increasing the mole fraction of B. Clear? So you have a composition C1. That means අපි හිතමු X A is equal 70%, 75 කියලා හිතන්න. 75%. Clear this point. You have more A. Right? So now how do we differentiate these two? So you take that composition. You slowly increase the temperature. Now here, this side, you are increasing temperature. Slowly increase your temperature. What will happen at this point? You have whole liquid part here. Why? At low temperature, you have liquid. At this point, what will happen? The first first vapor particle appear. Right? So here in between these two, you have liquid plus vapor. Clear
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Give me 1 second. 1 second. Right. Sorry, I got a call, right? Okay. So now, what will happen here? So the first vapor particle appears. So when you are going towards this, again increasing temperature at this, after this point, you have only vapor here. Clear is it clear?
Yes, ma'am. Yes, ma'am.
Right. So now take this vapor out. And so you have here the liquid plus vapor. First vapor particle appear වෙච්ච ගමන් you have to get the vapor composition from this line. Right? So that vapor composition is rich in B. What is the composition? C2 composition. Right? So take that vapor out. Once it vaporizes, get that vapor out, which is rich in C2, and then it decrease its temperature. Right? So at this point, the first liquid appears. And again, at this first composition, take the vapor out. So this is the vapor composition. Now your vapor is becoming rich in Munada, B.
B.
Why? We are coming towards this side. Right? And again, likewise, at the end, after the steam distillation, you will be ended up with POB. Right? And from this end, you will be ended up with POA from the liquid end. Right? So for ideal binary solutions, binary means two component. Ideal solutions, when they steam distilled, you can obtain POA and POB from the after the distillation. Is it clear? Is it clear, everyone? Clear the හැමෝටම? Make a
madam.
clear the
Madam,
දරුවෝ?
can you explain again?
අයෝනේද?
Oh, madam.
Right. C1 composition එක ගන්න. C1 composition එක අරගෙන temperature වැඩි කරන්න. Right? So you are having this is called the liquidus curve. This curve is liquid composition curve. This curve is the vaporous curve. Right? So now take that composition and this liquid having C1 composition. And keeping temperature constant, you get the vapor of that. So can you all remember the steam distillation කරන්නේ? You can heat it inside a flask, right? You have a condenser here. And you can collect your solutions here, right? Clear so likewise.
Yes, madam.
So when you have A and B mixture, so that is your C1 mixture, right? So you have here your C1 mixture. You collect your vapor here, vapor from this, right? So that means your vapor composition, plastic this container, you have C2 composition. Clear? Is it clear?
Yes,
Now
madam.
take the C2 composition out. Make collect කරගන්න. And decrease its temperature. එයාගේ temperature අඩු වෙච්ච ගමන් you will get the liquid having the same composition. Clear? මේ vape එකේ liquid දැන් අපි when it goes towards the condenser through the condenser, you can collect the liquid here. This liquid can be collected having the same composition of this vapor. Clear?
Clear, madam.
Right. So now again, now put this C2 into this. Second time, add C2 into this. And do the distillation again. So you can collect your C3 now. Right? So likewise, this can be several times during the steam distillation. You will be able to separate out POA and POB from this end. Clear? Is it clear? So that is called the fractional distillation. In the fractional distillation column, you have different plates. Likewise, right? So that plate, you will have C2 composition. When it goes to this, it's having C1, C3. So at the end, you can collect POA and POB separately. Right? Is it clear?
Yes, madam.
Yes.
Okay. So that is binary ideal solutions, which obey the Raoult's and Dalton's law. Right? So now there can be solutions which does not obey the Raoult's and Dalton's law. So they called as azeotropic mixtures. Right? So for azeotropic mixtures, you can observe this type of mixtures, right? So these are non-ideal binary mixtures, right? So where it can form in between the composition when A and B mix each other. In between, it can form a constant boiling mixture, right? So that means non-ideal, right? Mixture. So that cannot be separate out POA and POB from the steam distillation, right? So you can have separate out POA, either POA with azeotropic mixture. So this point is azeotropic mixture. Either POA with azeotropic mixture or POB with azeotropic mixture. Clear? So these are called non-ideal mixtures or azeotropic mixtures. Right? So these are ideal mixtures. Clear the? So this can be positive deviation or this is negative deviation from the Raoult's law. Right? So you read them, right? හොඳට කියවලා බලන්න, you might understand this. So that means it can make, there are certain mixtures which can form positive deviations from the Raoult's law and negative deviations from the Raoult's law. Clear? It might not very clear to you, but however, with this knowledge, try to understand further. Okay, so now again we have two components. Now the system is solid liquid, right? For a solid liquid, you can form a eutectic composition, right? So what is eutectic composition? It's the lowest melting point attained by the mixture, right? So let's see. This is for the eutectic, solid liquid equilibrium. Now we are studying solid liquid equilibrium, right? That means, what do you have here on top of this line? 100% A or 100% silver here. What are the two solids? Silver and lead, right? So on top of here, 100% lead, right? So from here to here, you are adding certain amount of lead into that. So that means mole fraction of lead is increasing from here to here, right? So at this point, you have 100% silver, and in between these two, you have how many phases? How many components? May lines දෙක අතර. On top of this line, how many components you have?
One component.
You have only one component. Why only lead? Silver is there, right? Make out one component. However, in between these two, how many components?
Two.
Huh? You have
Two.
two components, right? So you should be able to apply the phase rule, right? So now let's see what will happen when we add somewhere here. That means your mixture consists of more silver, less lead, right? So slowly increase the temperature. Why? Temperature is this side, right? So at this point, during this part, you have both solids, solid A and solid B. Both are solidified separately. So how many phases? මම කලින් කිව්වා calcium carbonate.
Two.
Huh?
Two.
Two phases. How many components? In between these
Two
two lines,
components.
two
Oh.
components. Two phases, two components, right? So at this point, the first liquid particle appears. Is it clear? So here you have solid plus liquid. After that, you have all liquid. At high temperature, you have liquid. And so let's
Excuse me,
move.
madam.
Huh? Yes.
Madam, can you please define eutectic mixture once again, please?
Yeah. Okay. So eutectic point appears for solid liquid equilibrium. Harida. Solid and liquid equilibrium තියෙනවා. However, these are two component system. What are the two components here? Silver and lead here. Right? Those two mix to each other. Right? So somewhere here at higher temperature, solid the තියෙන liquid the. What do you have?
Liquid.
You have liquid here. So starting from this point, what do you have?
Liquid.
Starting with this composition. You have lead and silver together in this liquid composition. The composition is this. Let's see, it's 40% silver, right? So this is your composition. They all are in one liquid. However, you decrease the temperature slowly. You are moving down. So what will happen here? මෙතනදි මොකද වෙන්නේ? At this point, the first solid silver particle. Now you have much more silver here. The amount of silver here is
high.
Towards this side, increasing lead. No, this has to be 40% lead. Make a lead වෙන්න ඕනේ, not silver. Hey, හේතුව, you have 100% silver here now. Let's see, this is 40% lead here. Sorry. PB. Why? Towards this end, මොනවද වැඩි වෙන්නේ? Lead වැඩි වෙන්නේ. අපි හරියට half center එකේ ඉඳන් පොඩ්ඩක් මෙහෙට. That means you have 40% lead here. Clear there?
Yes,
Is it clear?
Yes, ma'am.
So at this composition, what do we have more? 40% lead, 60% silver. So that means at this point, the first silver particle appear. Why? You have more silver. It's easily solidified. So after this, in between these two, you have solid and liquid both. Clear? So which is solidified first? Solid, silver plus liquid. In between these two. However, at this point, the first lead particle is also appears. Clear? Metanadi first silver particle. Here, the first lead particles appear. So, in between these two, you have both solids. What are the two solids? SA and SB. Silver and lead. Right? Is it clear? So, the eutectic point is the lowest temperature at which the liquid and both solids, liquid and solid A and solid B, lead and silver are in one equilibrium, the lowest temperature. Because what will happen? When we mix an impurity, that means you are increasing the impurity. right? 1 minute. Clear? Is it clear now? So this is the eutectic temperature and this is the eutectic composition. This is eutectic temperature, right? This temperature. And this is composition. Lead 97.4, silver 2.6 is the eutectic composition. Is it clear now?
Madam, which part is
Yes,
the
madam.
first solidifying liquid? Sol
Mokada? Yeah. So let's come from this one, right? So here you have all liquid. So slowly bring the temperature down. So at this point, the first which solid appears? Descent,
lead.
more
Lead.
lead is there. So the first solid lead appears here, right? After that you have liquid plus solid lead, right? Solid lead plus liquid, right? And at this point, both solid appear, right? So that's why at this particular composition, right? Liquid and both these three are in one equilibrium. So this is not, however, so the eutectic point is the lowest temperature. Aduma temperature. This is the lowest temperature at which all three are in one equilibrium. Liquid and two solids. Is it clear?
Yes, madam.
Okay. So now you can go through further and try to understand the content in
Excuse
your
me,
book.
madam.
Yes.
So the freezing point depends on the composition of the
Yes,
of
of
the
course.
component,
That's what
the
why you
concentration.
do. Yes. So why do you
Okay.
add a little amount of salt into ice? Huh? Then you can keep, longer without dissolving. The solid ice, when you add impurity, that means you are adding salt, right? So you can keep it longer time. So what will happen? The freezing point decreases when you add so impurity or the salt here, right? Is it clear?
Yes, madam.
Okay. So now the two component mixtures and not only the melting of a compound, there are congruent and incongruent melting points, right? So incongruent melting point are the mixture. So binary system, two components. Binary means two components. Said to be possess a congruent melting point when it melts a sharp temperature to which a liquid of the same composition that of solid, right? And this generally happens in two components, right? Yes, Taruni. Putte. Okay. Now is it clear, everyone? Huh?
Yes,
Oh.
madam.
Okay. Now what are incongruent melting points? That means they form, this is the liquid concurrent melting point, right? So these are the eutectic points. Hello, Putte. Right? So these are the concurrent melting point systems. So certain solids may here this is what we have studied up to now. May one this point, eutectic point here. This is very much similar to one which we have studied here, and this is another system like that, right? May here. From here to here. This is another point, the eutectic point. So in between two eutectic points, there can be another point where you can form a liquid concurrent melting. Is called the concurrent melting point, right? So you can go through it again, right? So certain solids, when they mix each other, when zinc and magnesium mixing each other, it can form concurrent melting systems, right? So these are the types of, so for a given two eutectic points, you can have n-1 concurrent point. So that means there can be solid liquid equilibrium. You can have more than one. So here this consists of 3 eutectic points. So how many concurrent points? 3 minus 2. Sorry, 3 minus 1. How many?
Two.
Two concurrent points, right? So that is the concurrent point where that occurs in between two solids mixing. It can generate a concurrent, a binary system, which possesses concurrent melting point when melts at sharp temperature to give the liquid of the same composition, right? Okay. So you can go through your book and try to understand this. I will somehow send you the Google link for the course material, right? So I will email it to you, right? So that's all about the spectroscopy and phase equilibria. Have you learned anything new with this in these two lecture sessions? Huh? Unit
Yes,
1
ma'am.
and Unit 4?
Yes, madam.
So what do you want? I mean, what do you think? Having these type of day schools?
It's very useful, madam.
Yeah, what you want to do now without delay, please go through the course materials. So for the time being, the soft copies, and if the strike is over, you will be able to take your hard copies. So now itself start studying for the CAT exams, not only the CAT, just to understand the concept first, right? So because it takes long time for you to study these 4301, 4303 and 4300, right? It's little difficult for you to understand the concept certain. So start now itself. Clear? Is it clear?
Yes, madam.
Okay. So now what you can do, we'll take a small break, right? Dr. Kumudika, are you here? Dr. Kumudika?
Yes, I'm here.
All right. Dr. Kumudika is there. So actually, without taking any break, we continued with the second part of this lecture. So Do you want another break, a small break?
Madam, we have at 6 o'clock zoology, ecology one also. Yes.
It won't take
Yeah,
that
then
much time, no, Dr. Kumudika?
yeah. If I start now, then I can complete by 5:30. I need 1 and 15 minutes. 1 hour and 15 minutes is enough for me.
Right.
Then shall we start, ne? Yeah, okay.
Okay, I'm ending my this thing, right? So you wanted to start
Excuse me, madam.
again.
Yeah.
Yes. Recording, I'm going to stop it from here, Kumudika, right?
Okay.